A 2,400-year-old thought experiment from ancient Greece accidentally predicted how particles behave in quantum labs. From paradoxes that prove motion is impossible to ones that delete information from reality itself, these are the ideas that broke physics and never got fixed. We're covering all of them, starting with the oldest one on the list: Zeno's paradoxes. Around 450 BCE, a Greek philosopher named Zeno of Elea proposed something so stupid it's been haunting physicists for over 2 millennia. His argument was simple. To walk across a room, you first have to cross half the room, then half of what's left, then half of that. Forever. You'd need to complete an infinite number of steps before reaching the other side, which means, logically, you can't move at all. Aristotle heard this and immediately tried to debunk it. He documented Zeno's paradoxes specifically to tear them apart. And for a long time, everyone assumed he succeeded. Then calculus showed up in the 1670s and gave us infinite series convergence, which proved that adding up infinite shrinking intervals does produce a finite result. Problem solved. Textbooks closed, except nature didn't get the memo. In the 20th century, physicists discovered that if you continuously observe a quantum particle, it literally freezes in place. Won't decay. Won't do anything. They called it the quantum Zeno effect because that's exactly what Zeno described. Watching something prevents it from moving. Here's the thing. Calculus explains why the math works out. What it doesn't explain is why reality allows you to traverse an infinite number of subdivisions in finite time. The math describes the answer. It doesn't give you the reason. So Aristotle tried to kill these paradoxes 2,400 years ago, and they're still breathing. But if an ancient Greek breaking motion sounds bad, wait until you hear about the paradox that proves the night sky shouldn't be dark. Olbers' paradox. Here's a question that sounds stupid until it ruins your entire week. Why is it dark at night? No, seriously. If the universe is infinite and filled with stars in every direction, then every single line of sight should eventually land on a star. The sky shouldn't just be bright. It should be infinitely bright. Every square inch of darkness you've ever stared at should be blinding white starlight. You should be cooked alive just by existing. But you're not. You're fine. The sky is dark. And that seemingly boring observation is one of the most important pieces of cosmological evidence in human history. Thomas Digges noticed this problem back in 1576. Heinrich Olbers formalized it in 1823 and naturally got all the credit. But the core question remained the same. If space goes on forever and stars are everywhere, where is all the light? Here's where it gets wild. The answer to why is the sky dark accidentally predicted the Big Bang roughly 80 years before anyone confirmed it. The night sky is dark because the universe isn't infinite in age. It's 13.8 billion years old. Light from the most distant stars literally hasn't had time to reach us yet. The universe has an edge, not in space, but in time. And it gets better. The universe is also expanding, which stretches light from far-off stars so far that it redshifts completely out of the visible spectrum. The light is technically there. You just can't see it. It's been diluted into microwave background radiation, which is, not ideal for stargazing. So every single night you've ever looked up at a dark sky, you were staring at direct proof that the universe had a beginning. Nobody knew it for centuries. But if the darkness of space hides a profound truth, wait until you hear what happens when you try to put a ladder in a garage at nearly the speed of light. The ladder paradox. This is the paradox that makes physics students genuinely angry, and I completely understand why. Here's the setup. You've got a ladder, and you've got a garage that's slightly too small to fit it. Simple enough. Now accelerate that ladder to 90% the speed of light. At that velocity, the Lorentz factor kicks in at roughly 2.3, which means the ladder contracts to about half its resting length. It shrinks, it now fits comfortably inside the garage. You slam both doors shut at the same time, the ladder is fully enclosed, paradox over. Except no. Because in the ladder's reference frame, the ladder hasn't shrunk at all. It's the garage that contracted. The garage is now even smaller than it was before, and the ladder absolutely does not fit. Both doors cannot be closed around it. The ladder is sticking out both ends. So which is it? Does the ladder fit or doesn't it? Both. The answer is both, and neither observer is wrong. Here's where it gets genuinely maddening. The resolution comes down to simultaneity, which is physics' way of saying at the same time doesn't mean anything universal. In the garage frame, both doors close simultaneously and the ladder fits. In the ladder's frame, those same two doors do not close at the same time. One closes before the other, and the ladder passes through without ever being fully contained. The order of events literally changes depending on who's watching, not the interpretation, the actual order. This isn't theoretical hand-waving either. Particle accelerators observe contracted particles behaving exactly as relativity predicts every single day. The math works, the experiments confirm it, there's no true length of anything moving at relativistic speeds. Reality is observer-dependent, and if that makes you uncomfortable, I don't know what to tell you. But at least this paradox only breaks your intuition about space and time. The next one breaks causality itself. The bootstrap paradox. Imagine you travel back in time and hand Beethoven's complete symphonies to a young, unknown Beethoven. He studies them, copies them note for note, and publishes them under his name. He becomes the Beethoven we all know. You learned the symphonies from history books that credit Beethoven. Beethoven learned them from you. So, who actually composed them? Nobody, that's the answer. Nobody composed them. The music exists in a perfect closed loop. It has no origin, no moment of creation, no point where someone sat down and thought of it for the first time. Every note is accounted for, every event is logically consistent, and yet the information appeared from absolutely nowhere. Which is, not ideal. This is the bootstrap paradox, and it's fundamentally different from the grandfather paradox. The grandfather paradox creates a contradiction. You kill your grandfather, you're never born, so you can't kill your grandfather. It breaks logic. The bootstrap paradox does something arguably worse. It breaks nothing. Everything is perfectly consistent. There's zero contradiction anywhere in the chain. And that's exactly what makes it so unsettling, because something was clearly never created, yet it exists. Here's where it gets complicated. This isn't just science fiction hand-waving. Closed time-like curves in general relativity mathematically permit exactly these kinds of loops. The equations of physics look at this scenario and shrug. Nothing forbids it. The Novikov self-consistency principle was proposed specifically to handle situations like this, essentially arguing that any time travel event must be self-consistent, no paradoxes allowed. But here's the kicker. It's never been empirically tested. It might be untestable entirely. It's a rule we invented to make ourselves feel better about a problem we can't solve. And the deeper issue is conservation of information. Information, like energy, isn't supposed to appear from nothing. The bootstrap paradox violates that principle with a smile on its face. The symphonies contain enormous informational complexity. They encode musical theory, emotional structure, creative decisions. All of that complexity exists without ever being generated by a mind. But if information appearing from nowhere bothers you, wait until you hear about information being permanently destroyed. Loschmidt-Echo paradox. Every equation in physics works backward. Every single one. Newton's laws, Maxwell's equations, quantum mechanics, all of it. Flip the direction of time and the math still checks out perfectly. Particles colliding and scattering obey the same rules, whether you play the tape forward or backward. The fundamental laws of the universe do not care which direction time flows, and yet nothing ever happens backward. You've never seen a shattered glass leap off the floor and reassemble itself on the counter. You have never watched smoke pour back into a candle. The universe moves in one direction and one direction only. And here's the thing. Physics cannot explain why. This is what Ernst Loschmidt pointed out in 1876, and it still has physicists losing sleep. You could theoretically reverse every particle's momentum in a closed system, and the equations would hold. The universe would rewind with zero mathematical violations. It just never happens. Now, most people point to the second law of thermodynamics. Entropy always increases. Disorder grows. That's the arrow of time, but here's where it gets complicated. The second law describes the arrow of time. It doesn't explain why it exists. It's like saying clocks move forward because the hands go clockwise. You haven't actually answered anything. The real mystery is buried deeper. The universe began in an extraordinarily low entropy state, basically the most ordered arrangement imaginable, and everything since has been a slow slide toward chaos. But why did it start that way? Nobody knows. That's not a gap in our understanding. That's a wall. Some physicists think time's direction is fundamental, baked into reality itself. Others argue it's an emergent illusion, nothing more than statistics playing out across trillions of particles. Both camps have math. Neither has proof. We live inside a universe where every law says backward is fine, and every observation says forward only. And the honest answer for why? We genuinely do not know. Which is, not ideal. But if the direction of time unsettles you, wait until you hear about two particles that seem to communicate instantly across the entire universe because Einstein hated that one. The Fermi paradox. Every paradox we've covered so far breaks physics from the inside. This one breaks you. In 1950, physicist Enrico Fermi sat down for lunch with colleagues at Los Alamos, and somewhere between bites, he asked a question nobody has been able to answer since. Where is everybody? Here's the math. The Milky Way contains somewhere between 100 and 200 billion stars. Many are billions of years older than our sun. The Drake equation, which estimates how many civilizations should be broadcasting signals right now, spits out a number in the millions. And SETI has been scanning the skies since 1960. Over 70 years of listening, confirmed detections, 0. The knee-jerk response is always distance. Space is big. Signals take forever. We just haven't looked long enough. But here's the thing. The paradox already accounts for that. Even at a fraction of the speed of light, a single civilization could colonize the entire Milky Way in a few 100 million years. That's a rounding error on cosmic timescales. Somebody should have shown up by now, which means every possible answer is terrifying in a different way. Option 1. Intelligent life is extraordinarily rare, and we are essentially a cosmic miracle alone in a galaxy of dead rocks. Option 2. Civilizations arise all the time, but consistently destroy themselves before they ever become detectable. Nuclear war, climate collapse, artificial intelligence, pick your favorite. This is the Great Filter hypothesis, and the uncomfortable question it asks is simple. Is the filter behind us or ahead of us? Option 3. Something else entirely. Something we haven't thought of. Which is, not comforting. Every other paradox on this list has a proposed resolution, even if it's unsatisfying. The Fermi paradox doesn't even have that, just silence. And silence, it turns out, is the loudest answer of all. But if the emptiness of space unsettles you, wait until we turn the camera back toward the smallest things in the universe, because quantum mechanics has a paradox that might prove reality. Itself doesn't exist until you look at it. The predestination paradox. Most time travel paradoxes break the universe. This one doesn't, and that's exactly why it's terrifying. Here's the setup. A man discovers that World War I is about to happen, so he builds a time machine, travels back to 1914, and tries to prevent it. He makes different choices, moves different pieces, changes the sequence of events. And when the dust settles, he realizes his actions didn't prevent World War I. His actions caused it. Every single thing he did to stop the war was already part of the chain of events that started it. He was always there. He was always going to be there. History didn't change because it was never different. This is the predestination paradox, and unlike the grandfather paradox, it doesn't create a logical contradiction. It creates perfect logical consistency. Everything lines up. The timeline is clean. There are 0 errors, 0 plot holes, 0 broken laws of physics, and that's the problem. Because if your time travel was always part of history, then you didn't choose to go back. You were always going to go back. Your decisions in the past weren't decisions at all. They were predetermined actions that your future self was always going to take, because your future self already took them. Free will doesn't just get challenged here, it gets deleted. The Novikov self-consistency principle actually supports this. It proposes that the universe would enforce a single consistent timeline, meaning any attempt to change the past automatically becomes part of the original sequence. You can't create a paradox because the universe won't let you. Whatever you do was already done. Whatever you choose was already chosen. You're not a time traveler. You're a puppet replaying a script you wrote for yourself before you existed. Now, to be clear, this is all theoretical. Nobody's built a time machine. Nobody's tested the Novikov principle. This entire framework depends on time travel being possible in the first place, which remains firmly unproven. But as a thought experiment, the predestination paradox asks the single most uncomfortable question in physics. What if the universe is logically perfect, and the cost of that perfection is that nothing you do has ever been your choice? Most paradoxes scare you because something breaks. This one scares you because nothing does. But if losing your free will sounds bad, wait until you lose your entire reality. EPR paradox. Einstein designed this paradox to prove quantum mechanics was broken. He published it in 1935 alongside Podolsky and Rosen, and the argument was elegant. Take two particles, entangle them, then separate them by any distance you want. Could be across a room, could be across the galaxy. Now, measure one particle's spin. The instant you do, the other particle's spin is immediately determined, not after a delay, not after some signal travels between them, instantly. Einstein hated this. He called it spooky action at a distance, and he meant that as an insult. His argument was simple: if measuring one particle instantly affects another particle light years away, then either information is traveling faster than light, which violates relativity, or quantum mechanics is missing something. There must be hidden variables, some deeper layer of reality where the particles already decided their properties before anyone measured them. Like two gloves shipped in separate boxes. You open one and see a left glove, so you know the other is a right glove. No spookiness required. It was a brilliant argument. It was also completely wrong. In 1964, physicist John Bell did something nobody expected. He created a mathematical theorem that could actually test whether hidden variables existed, not philosophically, mathematically. Bell's theorem proved that if hidden variables were real, the correlations between entangled particles would have a hard upper limit. Quantum mechanics predicted correlations beyond that limit. So you just had to run the experiment and see who was right. The experiment started in 1982 with Alain Aspect's team. The correlations exceeded Bell's limit. Quantum mechanics won. Einstein lost. And in 2022, Closer, Aspect, and Zeilinger won the Nobel Prize in Physics for proving it beyond any reasonable doubt. Here's what makes this genuinely unsettling. The results force you into one of two options. Either reality is non-local, meaning influences between entangled particles somehow operate outside the speed of light, or particles simply don't have definite properties until you measure them. They exist in a state of genuine indeterminacy. Both options demolish everything classical physics assumed about how the universe works. And before anyone gets excited, no, you can't use this to send messages faster than light. The correlations are real, but they're statistically random until you compare results through normal channels. The universe apparently has no problem being deeply, fundamentally weird, but it draws the line at letting you exploit it. Which is, not ideal. But if entanglement breaks your brain, wait until you hear about a paradox that threatens to break physics itself, one that even Stephen Hawking couldn't solve. Information. Paradox. In 1974, Stephen Hawking broke physics. Not in the fun way where you discover something new and everyone celebrates. In the way where you prove that the two most successful theories in human history cannot both be true, and then you sit back and watch the entire field panic for the next 50 years. Here's what he found. Black holes aren't permanent. They emit radiation, now called Hawking radiation, at a temperature inversely proportional to their mass. And as they radiate, they shrink. Given enough time, a black hole will evaporate completely. Gone. Nothing left. Cool. Except for one enormous problem. The radiation that escapes carries zero information about what fell into the black hole. None. A black hole could swallow billions of stars, entire civilizations worth of matter, every atom perfectly encoded with quantum information, and when that black hole finally evaporates, all of that information just vanishes. Poof. And that violates the single most fundamental rule in quantum mechanics. Information can never be truly destroyed. You can scramble it, you can shuffle it, you can make it practically impossible to recover, but it has to still exist somewhere. Every equation, every prediction, every experiment that's ever confirmed quantum theory assumes information is conserved. Hawking's calculation says it isn't. So now you've got general relativity saying black holes evaporate, and quantum mechanics saying the information inside can't just disappear. Both theories are confirmed to absurd levels of precision, and they directly contradict each other on this one point. The proposed solutions are wild. Firewalls that incinerate anything crossing the event horizon. Soft hair on the black hole's surface that somehow encodes information. The holographic principle, which suggests everything inside a black hole is actually stored on its two-dimensional surface like a cosmic DVD. Each one more mathematically creative than the last, none of them testable with any technology we currently have. Hawking himself changed his position multiple times. He initially said information was destroyed. Then he conceded it might survive. He never settled on a final answer before his death. And here's the thing that makes physicists lose sleep. Solving this paradox will likely require fundamentally rewriting either quantum mechanics or general relativity. One of the two pillars holding up all of modern physics has to crack. We just don't know which one. 50 years of the brightest minds in theoretical physics, and the answer is still, we genuinely do not know. Which is, not ideal. But if an unsolved war between two theories sounds heavy, wait until you hear about the paradox that questions whether we're alone in the entire universe. Quantum suicide paradox. This is the one that's going to follow you home tonight. In 1987, a physicist named Bruno Pigot proposed a thought experiment so disturbing it's been making people lose sleep for nearly 4 decades. The setup is simple. You sit in front of a device that measures a quantum event with a perfectly random 50-50 outcome. Heads, you live. Tails, the device kills you instantly. You press the button. In any normal understanding of probability, your chances get worse every round. After 10 trials less than 1 in 1,000, after 50, your odds of being alive are so astronomically small, they might as well be 0. You are, statistically speaking, extremely dead. But here's where many worlds quantum mechanics walks in and ruins everything. If the many worlds interpretation is correct, every quantum event has all outcomes simultaneously, each one spawning a real branching universe. When you press that button, the universe splits. In one branch, you die. In the other, you survive. After 50 presses, there are trillions upon trillions of branches where you're a corpse. And exactly one impossibly narrow thread of reality where you're still sitting in that chair, blinking, wondering why the device seems broken. Here's the kicker. Consciousness can only exist where it survives. Dead versions of you don't experience anything. The only version capable of having any experience at all is the one that made it through every single trial. From your perspective, you survive with absolute certainty. Every time. Forever. That's not an immortality in any comforting sense. Countless versions of you are gone. But the one who can still think, still observe, that version always pulls through. And this is where it gets truly unhinged. You cannot test this ever. The only person who could confirm quantum immortality is the subject, and they can never report a failure, because failure means death. Outside observers just see a person who got lucky once and then died. The experiment is unfalsifiable by design. It's not just unsolved, it is unsolvable. Some physicists argue this is a genuine consequence of many worlds. Others say it's proof that many worlds must be wrong, because no sane interpretation of physics should produce subjective immortality as a side effect. Nobody has won that argument. Nobody can. And the most disturbing part? If many worlds is correct, you don't need the device. Every moment of your life, quantum events are branching. Car accidents you narrowly avoided. Cells that almost became cancerous but didn't. In some branches, those things killed you. But you're not in those branches, you're here. The version that made it through every single fork, you might already be the astronomically unlikely survivor, and you would have absolutely no way to know it. If you enjoyed this video and want to see more, click the video on the screen now.